those. Okay, let's dive into our problem one. So this company uses multiple types of robots to perform the material handling. And actually, when I joined my PhD program, my advisor and his team have been working on these type of problems for some time. So they had multiple papers and they had multiple patents also. And this company was actively implementing the solutions that they come up with. So when I joined, I got an opportunity to work on such a problem. So I am going to focus on that particular layout today. However, I want to let you know that robotic cells are very different. There are different type of robotic cells and different type of analysis you need to do in order to figure out what robotic arm or what robotic cell to use. Although my focus is just on one in order to make this like a more educational. So why it is very important to look into this problem? So these companies that use robotic arms or robotic cells for manufacturing, they tend to be like very precision-oriented industries, and the robo arms are highly expensive. Therefore, the improvements that you can achieve convert into millions of dollars at the end of the year. So even a small improvement you can actually achieve through scheduling and your investment decisions going to convert into a huge like impact on the bottom line. So robotic cells are seen in various industries. I'm not going to go over every single one of them. The company that I'm talking about, they are working on semiconductor wafer fabrication. So these are again high precision machining operations. So therefore, and high precision and high costly operations. So that is why it is important to figure out what is the best way to schedule the robots and which robo arms to purchase. So typically, these industries follow flow shops. I am hoping that you understand how a flow shop works. Let me give you a quick overview of a very simple flow shop. Okay, they can vary. So a simple flow shop in a robotic cell or otherwise, they actually produce like one single type of part, and each part follow the same order of processing. And you can assume there are no buffers, but of course you can have buffers. So in this case, in the simplest form, there are no buffers, no intermediate storage. So each part going to be either on a machine. If you are using a robot, the robot can hold the part, or it might be in the input buffer or the output buffer. So you think about two conveyor belts, one is feeding in and one is taking out the processed parts. So input output buffers are there. Other than that, there are no intermediate storage units. And each machine can hold one part. This can vary. You can have multiple machines, so then it becomes a parallel shop. So in a simple flow shop, let's assume there are no parallel machines. And the robot can hold at most one part. Actually, again, this can be relaxed. The robot can hold more than one part based on how many grippers it has. So in the simplest form, let's assume that there's only one part. So this is a very simple flow shop setup. So if you haven't seen how a robot work, I'm going to show you two videos, and then for two different purposes. The first one, I want you to see how the robot moves. This particular robot can move 360 degrees. And in the second video, you will see two different types of robo arms. So I want you to see why these purchasing decisions or investment decisions on different type of robots going to matter. So let's take a quick look at the first one. Okay. What you observe here is a single gripper robo arm, which can actually move 360 degrees. So let's take a look at the second one.
Oswald Jensen is an over 100 dual gripper solution, which compared to the single gripper, increases the productivity on the CNC machine simply by being able to handle two objects at the same time. We realized that with yet another cost-effective investment, we could improve our productivity even further. To sum it all up, we intend to invest further to ensure that we take full advantage of the collaborative robots. To sum it all up, we intend to invest further.
So here, let me go back. So here actually they are showing two different type of robo arms. One is a single gripper, the first one, and the second one is a dual gripper. So the only difference is that the dual gripper has two grippers and then it can rotate around its axis. So it can hold two parts and perform loading and unloading at the same time. However, single gripper has only a single, of course, only single gripper, so it can only handle one part. So if we were to unload a part, then it has to take it to another machine and load it before coming back to a different machine. So you can see here they are comparing the time to perform the same sequence of activities using the two different robo arms. And you can see the single gripper takes roughly about 12 seconds, 12 seconds more than the dual gripper. So you might think that 12 seconds is nothing. Actually, it is a lot because these are these are expensive units. And then if you can increase the number of units you could produce during a day, that is going to impact your bottom line. So 12 seconds is a big deal. So this is the main reason for utilization of different type of robo arms. And of course, by how many seconds you can improve your basically the cycle time depend on the type of the products you produce and what type of sequence they are going to follow. So since you now saw two different type of robots and how the robo moves, let's look at the business problem. So you might encounter a business problem like this. Suppose you are working for a company. It can be semiconductor or otherwise. So suppose the company is trying to purchase a robo arm, and the manager comes to you and then asks, could you please let us know how much impact this new robo arm going to have on our bottom line? Or is this a worthwhile investment? So if someone asks you this question, I mean, you may think that, oh, it has nothing to do with me. It's just an investment decision. Actually, it is not. You have to compare what is the investment and what is the impact of this investment on my bottom line, and what can it bring to my company? What can it do extra? So why is it better than what we currently have? So in this company, the question was whether to invest in a circular robotic cell. They were using linear robots. And a linear versus circular, the question was that is it worthwhile to invest in a circular robo? Obviously, circular robo is more flexible than linear robo. I will show you how they look like. But the company wants to know how much cost savings they can achieve, or how much increase in revenue they can realize due to this investment, simply because circular robots are more expensive than the linear robots. So that is the question, the managerial question that you are going to face, and your task is to provide them with a recommendation. So whenever a manager asks you a question, you have to back up your recommendation with some money. So if you simply do hand waving and give a lot of qualitative factors, yeah, they are valid, but if you show them money, most of the time it works. So you have to give some numbers. Either you have to say our productivity would improve by this percentage, or our profit might go up by this much. So some numerics should support your decision. So one way to approach this question is to do our typical cost benefit analysis. Costs are easy to figure out. You can look at the machine's lifetime, initial investment, requirement for the repairs and maintenance. These are very well scheduled maintenance programs. So you can easily figure out the cost associated with this investment over next few years. The second part of the analysis is to quantify the benefit. So you have to somehow figure out what is the increase in cash flow over the years. And this is where we get stuck, because we have to really ask what is that increase. So there are various methods. Once you figure out costs and benefits, you might have heard of payback method, net present value, and you can use expected value analysis, or any other analysis that you know of. You can actually make use of them and make your decisions based on that and support those with all the qualitative factors. So we know the costs, we don't know the benefits. So in this case, our main question was to determine the benefit due to adoption of the circular layout. So we simply ask, how are we going to quantify the increase in revenue due to this new investment? Then we obviously saw that there's no direct impact on the demand, because we are not doing a marketing campaign here. This is just an internal replacement of machines, and it is going to impact my cost structure or maybe my production, but not directly the demand. As you saw earlier in the video, this may have a significant impact on the throughput, because you cut down on the time that you take to perform sequence of activities, so you can produce more and more units. Typically, demand is not the problem in this industry. It is supplying these items as fast as possible. So if you increase your production, you can actually convert it into revenue. So this entire problem actually reduced to quantifying the throughput. If I know the throughput increase due to adoption of the circular layout, then I have a way to quantify my revenue. Then I can convert that into profit. So our benefit analysis now reduced to figuring out the throughput from the circular layout and the linear layout which they have been using, and compare the two to figure out what is the increase in throughput, so that I can calculate the cash inflow over the years. So as you may have guessed, these cells are very expensive. Therefore, once you adopt one particular layout, you are going to use it into the foreseeable future. So this actually allows us to perform a steady state analysis. So what is that? Suppose that you use a machine just today and you use something else tomorrow. Then you will not observe in a Flowshop setting the steady state. That means same type of activities happening again and again. So if you allow for a certain time period to lapse, then you can actually achieve the steady state, and we can perform the analysis assuming the steady state. That makes things much easier. Then choosing the layout, in this case, we have our linear versus circular layout, and we have to pick the best among them by looking at the increase in throughput. So before going into the details of how to quantify the throughput, let's understand the difference between the two, so you will see why circular layout has more flexibility. So this is a linear layout where you have an overhead robo arm which is performing the material handling. All the machines are like arranged in a linear fashion. This is a semicircular layout. From mathematical analysis wise, this is equivalent to the linear layout. Here the robo is in the middle, and all the machines are arranged in a semicircular fashion. And linear versus semicircular layouts, they are practically the same when it comes to mathematical analysis. So this is the proposed layout, circular layout. The robo is in the middle and the machines are around it. You can see the input and output buffers. So here the movement wise, the robo can actually save time. So just to give you an idea, if the robo wants to go from input to output, it simply has to move between the two machines. However, in the linear layout, it has to go over all the M machines to get to the output buffer from the input buffer. So you can actually save in terms of the travel distance here. So at least you can see the flexibility of the circular layout in this case. Okay. So let's recap our problem. So what is our goal? We want to compare a linear versus circular layout. What are the conditions imposed by the company? In this case, nothing specific. There are a few things that they were looking at. I'll come to that in a minute. But we had limited choices. It is just because it makes the analysis easy. However, as I mentioned, there have been numerous papers or numerous projects analyzing various different type of layouts. So this is just one piece. Okay, so this is one piece to a like much a larger problem. So what are we comparing? We are comparing the throughput. So the question is that how are we going to quantify the throughput? So what about the linear layout that they have been using? Of course, you know the throughput because they have been using it. Look at the historical data. You can simply figure out what is the throughput for the existing system. And not only that, the linear layout that they have been using also it has been analyzed thoroughly, and there is a theoretical way to calculate the best throughput from a linear layout. So it was not an issue. We knew what is the throughput from the linear layout. Either look at data or do it analytically, doesn't matter, there was a method. However, for the circular layout at that time, there was no method to calculate it, and there was no historical data to look at. So now the question reduces to quantifying the throughput from the circular layout. So our plan, find a way to calculate the throughput from the circular layout, then calculate the linear layout throughput using observations or using the exact method which already exists. And based on that, develop the cash flow inflow for both layouts, figure out which one is better, and compare the two investment decisions based on whatever the selected method, payback method, NPV, or expected value method. So any method you want to use, you can use them to make the investment decision after that. Okay. So as soon as we actually reduce our problem to quantifying the throughput for the circular layout, the first question that comes to your mind is that, is there a method to calculate it? As I mentioned, there was none at that time. But if there is a method, still you have to ask the following questions. Is that method an exact method? That means, do you know how well you can do it? If you don't have the answer to that, you can ask, is there any heuristic or a simulation that exists to calculate the throughput? However, you have to be mindful if you are using a heuristic or a simulation, they are going to give you an answer based on what you input, your rules. So rules are determined by you or someone else, of course, and the quality of your output depend on those rules. So how you develop a heuristic or a simulation matters a lot. So you will see the heuristic development example in the second problem when we move on to our problem number 2 later. So then obviously we try to find easy ways out. So is there an easy way out for this problem? Can I figure out the throughput without doing much analysis? Don't do any math. So let's figure out the easy way. The easiest way to do this is to take the existing schedule or existing sequence that you are using in the linear layout, do exact same using the circular layout. Okay? So if you do that, because the circular layout is more flexible, you know that it's going to be definitely better than what you are getting right now. Right? Everything that you can do using the linear layout, you can do using the circular layout. So there is no question this is going to be better. But this is a very lousy answer because it is not allowing you to understand the potential of the layout. So it's not good enough. And remember, these are very high precision operations, and processing time improvement is in seconds. So if you are not actually quantifying it correctly, you cannot make a good decision. So even if you were to use very simple simulation, you have to determine how am I going to simulate this cell, right? What are the rules, and how am I going to even come up with these rules? So because of that, you have to take a closer look at the structure of this cell and understand it and develop some set of rules. How am I going to perform my the sequencing of the robo arm movements to get the true potential of this investment. So in order to do that, we actually looked at first the inputs. What do we know? What about the process itself and the robo arm and its abilities? So there are various things you have to look for. Again, this varies from problem to problem, but in this problem, we have to understand the robo or the circular robo. So we ask how many grippers does it have? It had a single gripper. It had a single gripper and time to move between two machines. And there's something called constant time movement additive Euclidean. You don't have to worry about this. And in this robotic cell, it's additive time. I'll show you what is the meaning of that in a minute. Then you have to ask what is the time the robot takes to load or unload a part. So these are the things that you have to understand when it comes to the robo arm itself. Then you have to understand your own process. When it comes to understanding the process, you have to ask how many machines are you going to put into this cell and what is the sequence, um, machining time of a particular part on each machine, and ability of the machine to perform multiple tasks. In this case, it could perform only one task at a time. Then there is something called part pickup criteria. That means suppose that you load a part and machine is processing it and then it finishes processing. Can you leave the part in the machine for some time? Sometimes it's not possible because the part may get heated up, it might damage it. Sometimes you use certain type of chemicals and it can damage the part. So you cannot leave the part on the machine, you have to take it out. So that is called no wait. You process, you take it out immediately. Sometimes there is some interval, a safe interval that you can leave the part. So it is interval pickup criteria. Sometimes it doesn't matter. So that is called free pickup criteria. So you have to understand this about your own parts and the production process. Then of course you have to ask whether there are buffers or not. So these are the things you have to gather in before even attempting to do this analysis. Then we need one theoretical result. Again, don't worry about understanding what it is. It simply says that it is sufficient to look at cyclic schedules. That means repetition of sequence of activities again and again. So it is proven mathematically that cyclic schedules are always better than any other sequence. Okay? So at the end of one cycle, one cyclic schedule, you can produce one parts, two parts, three parts, or k number of parts. If you can produce k number of parts, we call it a k unit cycle. And if you produce a single part, we call it a 1 unit cycle in robotic cells. So we are going to focus on 1 unit cycles for various reasons. First of all, 1 unit cycles have limited number of activities. Second, in most of the practical cases, these are optimum. You don't have to look at k unit cycles. It's sufficient to look at 1 unit cycles. Third, they are easy to implement. I know that I have practitioners in the audience and they would agree with me, more complicated the solutions going to be, harder to implement in practice. So you need simple and elegant solutions that can be implemented. So 1 unit cycles are very good and they are easy to implement. So we are going to look at 1 unit cycles. So for this particular talk, this particular analysis, actually we looked at 1 unit cycles. I gave you all the reasons why we like them. And there were many other things we gathered during the process. We realized we know the processing times deterministically. It's sometimes you may not, but in this particular case we knew. Simply because this is semiconductor wafer manufacturing, they know everything with very high precision. So we had our processing times available for the analysis. Second, our machines were non-preemptive. That means if you put a part into a machine, you have to finish processing it. You cannot take it out and put it back. Those are called non-preemptive schedules. So our setting was non-preemptive. We cannot take a part out and put it back. That is not like allowed by the company. Um, Fourth one, parts available all the time. So this is an assumption because otherwise it basically saying you are not efficient. You don't have enough parts to produce. Then why would you try to improve the throughput in the first place, right? So we just assumed we have parts in our conveyor belt keep on giving us one part after the other that needs to be processed. So that is an assumption. And I think it's a realistic one. Parts are identical. This is typically the case because you don't use robotic cells for like one part. Let's say you do part A first, then B, then C, then D. Then you don't do that. You produce one type of parts, then you can change the type of part that you produce. The company had free pickup criteria. That means we can leave the part on the machine after the completion of the processing time. And we were looking at additive travel time cell, which I will explain in a minute. And there were no buffers in between. So you have to leave the part in the machine, or you have to keep it with the robo. And our robo had single gripper. It's not dual gripper robo. Okay. So you may wonder, okay, it seems like so many assumptions. Actually, only assumption I had there was input buffer has continuous supply of parts. Actually, I also assumed output buffer is always free. That means you can actually unload a part all the time. So these are the two assumptions. Everything else came from the features of the machine or features of the process or processing times, ability to predict them. These are all very unique to the company setting. However, if you want to relax any one of them, you can find analysis done for that because this is a very rich area and people are actively working in this area because there are different type of robots, different type of technologies. Every single day we see different variations. So there's a lot of work in this area. Okay, so you can look into those type of analysis if you are interested. So let me convince you that scheduling the robo movement is hard. So a simple example, suppose your cell looks like this. The white arm here, that is the robo, and you can see the machine's input-output buffers. Here you have two choices. First, you can unload the part, or rather doing that, you can go load the machine one. So in this simple setting, you have two choices. Now imagine you have about 20 plus machines and then parts are everywhere. You have so many different choices. So which one are you going to do first? As soon as you do one, your next choice set would vary. Then which one would you pick? When you do that, your choice again changes, right? So this is actually combinatorial, or this is going to explode the number of choices you have. So how are you going to analyze which choice are you going to implement first? Then what? Then what? So that is the sequencing of the robo arm that we are going to look at. Um, Here the parts, they move from machine 1, then to 2, then to 3, so on and so forth, because this is a Flowshop setting. The question is about sequencing the arm. Where would it go? Which machine would it go? Would it load, unload? That is the question that we are asking. Okay. So I need to recap what we are looking at because I gave you a lot of information. We are looking at cyclic schedules, 1-unit cycles, and free pickup cell with additive travel time. And in this analysis, actually, I categorized the machines into two groups. You don't have to, again, memorize what it is. So just imagine based on the travel time and the processing time, I identified a set of machines and named them set B. Okay, it's simple. Even if you look at it, it simply says the processing time on a machine is less than 2 times the travel distance between two machines. Okay, So here the travel time. So travel time between two machines here is delta. So additive travel time means that if you go from input to, let's say, machine 1, travel time is delta. You go from machine M1 to M2, it is delta. However, if you go from input to machine 2, it is 2 delta. Okay. So how the robo arm achieves it, it actually accelerate, then decelerate accordingly, and then it achieves this travel time. So this is the additive travel time. Some machines have constant travel time. Doesn't matter from which machine to which machine it goes, it's a constant time. Some have Euclidean. So you have A, B, C, the triangular inequality. So it depends on the features of the machine. So here it is additive cell. Okay, so I think that you are clear about the problem that we are analyzing. So we sat down, looked at this problem, and then we were able to show that finding out the throughput for this circular robotic cell is NP hard. Then again, I'm assuming that you know this word NP hard because I heard from your professors that you take a course and then you know what this means. So simply put, it's very difficult to solve using a commercial solver. So suppose that you sit down and do a mixed integer program, somehow come up with a mathematical formulation and give it to a commercial solver, it will not be able to solve it within a reasonable time limit. It would take days and days without giving you an answer. So that is a very crude way of explaining NP hard. It is much more theoretical than that. So basically, it's a hard problem to solve. So now what are we going to do? So we have a hard problem. We know that we cannot figure out the schedule exactly, but we need a good one. So again, we can go back to simulation, heuristics, or something called approximation algorithm. Excuse me. So approximation algorithm is the path we took because approximation algorithm allows you to understand the structure of the problem and you know for sure how bad your solution going to be. More than how good, you can say how bad. In the worst case, how bad your algorithm going to be. In a heuristic or a simulation, you do not know this. You do not know how worst you can perform, right? So you rely on your input and you think, oh, this is good. This is fairly good and I'm satisfied with it. But here we wanted to quantify it. The reason is as follows. Again, I'm going back to what I said earlier. These are high precision operations. Even seconds you save, going to save you a lot of money. So high precision you can get in your method, better it is going to be for the company. So we actually resort to approximation algorithm here. So we wanted a simple solution because we have to recommend this to the company. And if you give them a very, very complicated analysis and a very complicated answer, they will not be interested in implementing it. Moreover, it should be independent of the processing times. So you give me processing time for any part, then my solution should work. It should achieve the same approximation bound. So these are independent of the problem parameters. Okay, so let's say we have 3 machines. Your processing time might be 5, 10, 17. Second part, it might be 6, 12, and 5. So my approximation scheme does not depend on that. Okay, so that is what we were aiming for. So they can use this no matter what part they are going to put into the cell. They will achieve the same throughput increase and same same efficiency that we are claiming this algorithm could achieve. So to do that, we actually came up with 4 different cycles. Some cycles were similar to what people used for the linear layout, so we modified them. So it's only 4 cycles and they are pretty simple cycles. So to give you an idea about this entire robotic cell scheduling, if you look at 1 unit cycles, you can think of it as this one big circle. And our 4 cycles lie here. You can see something called loop cycles. It depends on my set B. And we have 2 specific type of loop cycles and 1 general one. So there are 3 different type of loop cycles. and something called this even odd cycle, pi c. It is not a loop cycle, but it is a very special type of a cycle. So these are the four cycles we used, and I'll show you quickly how they work, and you will see how easy to implement them. So the very first cycle says, simply load a part, wait there, unload it, load the next machine, and then just follow the part. Stay with the part. This is the forward cycle. This is very simple. Second cycle says, first load the odd machines. Okay, so I am loading odd machines, then load the even machines. Okay, so this is why this is called odd even machine. Load the odd machines first. So robo first go and load the odd machines, then it comes back and then load the even machines. Third one is the reverse cycle. It simply say load in the reverse sequence. So here is the steady state cell. So you keep on loading from in the reverse order. First you unload, then you load the machine 3, then 2, then 1. Okay, so then the cell comes back to the initial configuration. So loop cycle is slightly different. This is the most complicated one, and you will see how simple that is too. So let's look at the loop cycle. Here I have to categorize my machines into two parts, set B and machines that are not in set B. So set B are the empty squares, and the ones that are not in set B are the purple color ones. So here the rule is very simple again. So look at the purple color cells and then look at that cluster. So the machine 1 is a purple color one. Take the machine before that and after that, input and the M2. Then treat it as a reverse cycle. So here, machine M4, 5, 6, 7, that is one cluster because my purple ones, one before that, one after that. Treat them as a reverse cycle that you saw earlier. So it looks like this. So you basically do the reverse cycle. Then in the intermediate ones, you do it like a forward cycle. Then this is again a combination of a reverse cycle. So this is, you can actually visualize it as a combination of the forward and the reverse cycle designed in a particular way based on the set B. Okay? So these are the four cycles we proposed. And we were able to show that these four cycles, the best among them, gives you 5/3 approximation. And this bound is asymptotically tight. That means you can create a theoretical instance where the solution given by the best among the four going to be 66% higher than the optimum solution. Optimum is the best you could do. So you might think, oh, 66% away from the best solution, that's pretty bad. Actually, it is not. First of all, in developing these approximation algorithms, remember you do not know the best solution. You don't know the optimum solution. So what do? You are minimizing the cycle time, or you are maximizing throughput, which is same as minimizing cycle time. And I think you know this from our little slow. So minimizing cycle time means you have to minimize your objective function, right? Cycle time. So you don't know the optimum solution, but you can develop a lower bound. So you simply say that your optimum solution going to be always larger than a lower bound. Okay. So whether this lower bound so close to the optimum solution or so far away depend on how good you are at developing it, right? But we know it's not the same. So what I am comparing is my lower bound versus my algorithm solution. Okay, so that distance is larger, right? So this is my optimum and the algorithm solution, it is smaller compared to the lower bound and the algorithm solution. So this 66% is between the lower bound and the algorithm solution. So we would expect actually our true performance to be higher than this. And the other thing is that this is a theoretical development. In practice, you don't see these awkward cases that you can create theoretically, right? When you are doing something theoretically, you are looking at all possible processing combinations, right? So you can have processing on machine 1 to be 1 and machine 2 to be like, I don't know, 100 units. Huge variation between them. This might not be the case in practice. So all those going to affect the uh, true value that you are going to realize. So this is the worst case performance. Okay. Okay, so we wanted to implement this solution and see how much improvement we can get. First of all, we had the processing times with us. So we created a lot of instances and saw that actually our algorithm is not bad. Theoretically, it can be as bad as 66%, but for all the instances we got, it's only 3.25% away from the optimum solution. Again, here optimum means based on the lower bound we developed because we don't know the true optimum solution. Okay, so it's going to be even better than this. So this is 3.25, so which is pretty good. So we are almost achieving the best possible sequence. And then we use this algorithm and then quantified the throughput. Remember, that's our goal. We want to figure out how much improvement we can realize. So we saw that improvement on an average is around 13%, which is actually huge. So over the linear layout, your throughput increases by 13% on an average. So you can convert this into money. Then you know the benefit. You can use that to figure out whether investment going to pay off or how many years would it take for your investment to pay off, so on and so forth. Okay. So I'm not going to do the analysis of that, but I just gave you all the parts that are required to solve this problem. So to quickly recap how you approach this, first we looked at the business problem. Then we actually started off with finance. We simply said, oh, it is an investment decision. We need cost and benefit. We figured out the costs. Then we asked how to quantify the benefit. Then we realized we need to figure out the throughput for the circular layout. Existing one we know. Then we realized there's no way to figure it out. Then we ask, can we use easy way outs? In this case, easy way out is not good enough because these are very expensive machines, high precision operations, and the improvement can be, I mean, even slight deviation may not actually give you an understanding about the true potential of the machine. So then we show that this problem is very hard to solve. Therefore, we resort to an approximation algorithm, again, because of the previous reasons. We came up with very simple 4 different cycles that the practitioners can implement and showed that these 4 cycles together can achieve a really, really good outcome. And it has the potential to increase the throughput by 13%, which is huge. Okay. So this is problem 1, and I can move on to problem 2. Let me take a quick look at the time. So this problem I'm going to go over a little bit faster because I want to leave you some time for questions. Ilankon, what is the total length of the webinar? Is it 1.5 hours or 1.5 hours for the presentation?
Yeah, we actually have 2 hours time, so you can continue.
Okay, so then I can go a little bit slower here. Okay. So this problem is very different than the first one. In the first one, the methodologies we used, it's actually discrete optimization and algorithm development. You saw that processing times and the sequencing, all these are discrete operations. And I mentioned that the combinatorial nature, based on one choice, the next state of the cell going to be different. So you have different type of choices to make. That is the combinatorial nature of the problem. So it's all discrete optimization. The next problem is very different than what you observed. Like give you the problem. So what do we know? This is a shipping network. Of course, it's a network. You can represent a network with nodes and arcs. Nodes are cities, arcs are loads. So we have a shipping network and we want to identify a sub-network, that means part of it, for which fleet of resources can be exclusively assigned. That's the keyword, exclusively, because those resources cannot be used elsewhere. That's the feature of the problem. And if this is not properly designed, you might allocate more resources than you need to. And the customer may not be willing to pay you a premium if you are saying, I'll handle one load dedicated. Why would they pay you a premium, right? So it should be substantial. So the Walmart should see, oh, 20% of my loads are handled dedicated. So I am willing to give you something more. If you can handle 50%, I'll give you more, right? So your dedicated piece should be big enough. So those are the issues, and that is what we want to achieve. So what is the approach? Somehow represent this problem with an appropriate formulation. Then understand the properties and the structure of this dedicated idea and represent them mathematically somehow. Then understand the properties of a good solution or the best solution, and then propose a method to solve it, exact or otherwise. So this is actual data. So every single point you see here, that's an origin or a destination in the network. So you can see that how big it is. And every single point, it's not just one origin, it can have multiple truckloads. So these are just unique nodes in our shipper's network, because we are going to draw a network for the shipper. Every single point is a city or a node in our network. Okay. So obviously I have been using the word network often because we are using network analysis in this case. So the real world data, we mapped it into a network, and then we use the network flow analysis to understand the properties and the structure. So this is a simplification just to make you understand what we are talking about. So every node here, think about it as an origin or a destination point. Origin is where the load is leaving, and destination is where it arrives. And each arc represent it's a lane, we call it a lane, but it's a load moving in a truck. And the number represent how many truckloads. Okay. So this is the typical shipping network. This is the third party shipping network for the Walmart. So this is Walmart's component. All the loads here are for Walmart. Now the shipper is trying to extract part of it and say that this is my dedicated piece. I'll guarantee these parts I'll handle as a dedicated service. That is the problem. So which ones are you going to take out? Okay. So for each movement, you have associated operating costs. Okay, so to move from city 2 to 1, there is a cost associated with it. 4 to 3, there is another cost associated with it. By the way, these costs are pretty standard. There are published rates here. This is a highly competitive industry, so you can actually find out these costs very easily. So here is a dedicated subnetwork. I'm using the abbreviation DSN. So dedicated subnetwork. Do you think this is a good subnetwork? Seems like enough loads, but if you really stare at it, what is the problem with this? Suppose that you send 50 truckloads from 2 to 1. What are you going to do with that 50 truckloads sitting here? Right? These are dedicated trucks. You can't use any other loads to take them back to where they're supposed to be. So you have to make them go without any loads to some city where they are required. You can send them back to number 2, they can send back to 5 or somewhere else, right? So if you just take out parts like this, you have to think about what is called asset repositioning. Think about people, the drivers. Maybe their home, let's say Mr. A is located in city 2. And you ask him to carry, like he's one like driver who's going from 2 to 1. Now he's stranded here. He has to come back. This might be like, I don't know, 2,000 miles. So he's stranded here. He has to come back with his truck, right? So you have to do asset repositioning. So that is the main issue. So if you take a look at like a very random network like that, you can understand what is the problem with it. So you need to think about asset repositioning because of exclusive use of assets here. So why this is not good? You have to ask this: how many trucks do we need? I mean, you can't simply add these numbers because that is going to be ridiculously high. You can use the same truck again and again, but how are you going to use it? How do we maintain them? You need to have somewhere some depots, right? So you have to take the trucks back to those depots at one point. So you have to keep track of those. Do we have good enough depot capacity? Suppose your solution plan to send 1,000 trucks, not 1,000, let's say 20 trucks to a particular depot, but that depot does not have capacity to handle 20. How do we reposition them? From where to where are we going to send these trucks? How costly is to perform repositioning? If you are going to send them without carrying any loads, that's called empty travel or deadheading. Deadheading is costly because it doesn't make any profit for you, but it's costly, right? So what can we infer from all this? We need conservation of flow. That means whatever comes into a node should go out. Okay, so if you don't have that, you have to think about repositioning separately. So we don't want that. We want repositioning within the system so that this exclusivity can be maintained. Okay, so in network flow, as soon as you have conservation of flow, it suggests you need collection of cyclic routes. We need cycles. You have to identify a cycle, put it into the dedicated network. So your dedicated network should consist of cycles. So that is what we learned from network flow analysis. Okay. So I just showed you a network which looked really bad, right? Because we had no way of repositioning. So to reposition, you have actually two different strategies that the company was using. They were using deadheading. Lane sharing is what we proposed. Deadheading is very common. That means you go from A to B, B to C, but you have to send the truck back to A. So you send it without anything. So empty travel, which is costly, no profit, just cost. Second method is that suppose you are sending something from A to B and the total amount of truckloads from A to B is 50. Don't put all 50 into the dedicated part. Put part of it. That means share the lane between the dedicated and normal shippers network. This actually going to be costly when it comes to administrative part of it, because you have to figure out what loads to be in the dedicated one and what loads to be on the regular network. And although I am analyzing this problem as a static network by looking at the overall demand over the contract period, you have to keep in mind that these are all dynamic systems, right? So the loads, there's no guarantee. They typically say that every week we need this load, but it can vary, right? There's no guarantee load's going to be exactly those numbers. So whenever they request a load, you have to figure out whether it is going to be in the dedicated or not if you use lane sharing. So that is the administrative burden that they have to carry here, which is actually costly again. Apart from that, they had other issues. Lane capacities. So if you say you can send trucks from A to B, how many trucks can you allow? Can you send 1,000 trucks within a month? 100, 20, what is that? So it depends on the ability of the depots to handle this many loads. Okay, so that is called lane capacity. Node capacity, that is how many trucks can be maintained at a node. Some nodes, they don't have depots, so the node capacity becomes, let's say, 0. Some nodes, it might be 1, 200. So you have to know what are those node capacities. These are basically based on depots. This shipper has like this operating post in almost every city. So they should have the capacity to handle these incoming and outgoing trucks. If you don't have such capacity issues, it's pretty easy. Set those capacity limits to infinity, so your problem will be fine. Actually, when we talked to the practitioners, that's what they were doing. So they actually set everything to infinity. They ignored the lane sharing and then took a solution, then adjusted it manually to represent all these constraints. So we included that into the problem. So we created 4 variations of the problem. Actually, it's not necessary. Looking at the last version is enough because that encompasses all the 3 above. The reason to do 4 is because we were aiming at a publication. So we wanted to look at different characteristics. And by looking at them, actually, we were able to come up with a good heuristic. You will see that how I am using these different analyses later. But these 4 problems are pretty simple. First problem said, forget about lane sharing, forget about deadheading. Simply look at cyclic routes. If you have cyclic routes, put them in the dedicated network. So I am taking the same shipping network. I have only one cyclic route. This one, 50, and you can see it's a cycle. And if you tell Walmart, I'll take care of only 50 loads for you. Sorry, 50 plus 50 plus 50, sorry, 200 loads for you. Okay. They might be happy, they might not be happy given the size of their network. They have a large network, you have to ask what is that percentage. Sorry, I never added the numbers. I think it might be like very low percentage. They might not be happy to give you a premium price for this. Problem PD says, okay, forget about lane sharing. Let's use deadheading. Okay, so we are going to do empty travel, which is costly for the company. So it's going to eat into your profit margin, but you may be able to get a larger network and demand a higher premium price from Walmart. So let's go for that. So here is a network that I randomly picked using deadheading. And if you stare at it, you will see the cycles. So let me show you. This is one cycle, which is 100. Here is the next one, 50. I have written the addition of those along the arcs. Here is the next one, which is 100. Here is the other one, 50. So this is actually collection of 4 cycles. Okay. And the third one, let's forget about lane sharing. Let's forget about deadheading. Let's do lane sharing. So you can see here, these 2 arcs are shared. 3 to 2, actual load is 150. You are putting only 70 in the network. And 2 to 4, actual load is 80. You are only putting 70 in the network. Okay, so that is lane sharing because 10 going to be handled in the regular network. 70 will be in the dedicated network. And here again, we have cycles. This is 70, this is 50, 2 cycles. So PDL, you can combine both. You can do a better job here, and it is a more general problem. So this is the most general format. Okay. So those are the shared lanes in this particular problem, and the dashed lines, that is deadheading. You can see it's low deadheading, but the number of shared lanes are like 4. Okay, so please don't read it. If you want to write this mathematically, the problem statement, you can represent it as a network flow problem. So you don't have to talk about dedicated shippers network, nothing. You simply reduce this to this particular like problem statement. It is simply a network flow problem. So we have a network GVA, and this is standard notation. V is the set of nodes, A is the set of arcs, and non-negative integers. M is the mileage of arc ij, D is the demand on arc ij, this is the arc capacity on arc ij, and node capacity un, and you have costs associated with them. So everything now network flow analysis. And what is the solution? You need a subnetwork SG. It is actually a part. So N is a subset of V, E is a subset of A. Okay? And we need the flow conservation. You can actually write it using an equation, mathematical equation. Xij are the loads, Yij are the deadheading. So this is called node balance or flow balance equation. When you learn network flow analysis, you will learn this. This is very like standard formulation. Then we have to put arc capacities and node capacities. Again, you will learn this in network flow analysis. And our objective is to maximize the profit or the cost savings in this case. So I just wanted you to understand that the problem we had, the shipping network, dedicated services, how we came from that point to here. Now it is a simple math problem. It's no longer our business problem. So we had a shipping network. We understood what are the components of the dedicated services. Then we asked, what does that mean? We understood that it means flow conservation. We need cycles. We have node arc capacities. Then we converted that into a mathematical statement, which is a network flow analysis now. Okay. So you can do a MIP formulation because you are familiar with this. So this is for problem PD. I am not doing for every single one, but I just want you to understand here, you can do this. So this is deadheading cost. This is cost savings due to dedicated part. These are the constraints. First one is flow balance. Second one, node capacity. Third one says that you include all the flow on a particular arc if you are using it in the dedicated network. And you have arc capacities, 0, 1 variables, everything. And I'm actually not taking time to explain it because that's not the goal. But if you want to understand it later on, please reach out to me. I'll be happy to help you out. The main reason is that we never solved it. So we did it in a very convoluted way. So this is problem PL. Again, you can do an MIP formulation for that. Sorry, let me go back quickly. So here you have like bunch of 0, 1 variables to make sure that lane sharing is captured, which is slightly tricky to formulate using 0, 1 variables. So that's why you see a lot of constraints there. It's simply to say that if all in, there is no cost, but part of it is in, there is a cost. So you have to formulate that using 0, 1 variables. Okay, so what is the next step? We had the formulations. You can think, okay, I can feed this into a commercial solver and get the answer out. By the way, I'm not talking about that such a simple network. Remember what I told you? There are 12,000 loads in my 12,000 plus loads in my network. So you are looking at, actually, I had 200,000 plus variables, I think. So huge MIP formulation. So if there is a commercial solver which can handle this, give us the answer, well and good. Feed that problem, get the answer out, right? You can be happy. Or you can use simulation. Again, the same question. What are the rules? How are we going to do this? You can use meta heuristics if you like, all these taboo search, simulated annealing, all these heuristic methods, but which one, how to develop it. So we thought, let's understand the problem first, then pick what we want to do in this case. First thing we did, we actually asked, can we solve this optimally? And then we figured out we can't. All these versions are NP hard. That means hard to solve. Not only that, these are called APX hard. That means, simply put, you cannot find a constant factor approximation scheme. So you cannot get that approximation bound that we got for the previous problem in this case. So it's very hard to solve these problems. And you can read about what is APX, hard, PTAS, all these are in complexity theory. And again, like, just forget about it. Just imagine problem is hard to solve. Not only that, it is hard to approximate also. My first problem, I was able to approximate. This one, forget about that also. Okay, so it's a very hard problem. What can we do? So we tried feeding into the commercial solver, obviously without like getting anything for many days. So it's not going to work either. So you need a method to solve this one. So we can do either heuristic or like some sort of like meta heuristic, simulation. But in this case, we knew the structure of the dedicated part, all these cycles. So cycles are a nice structure. So we thought, why can't we learn about them better? Then use that understanding to come up with a good heuristic. So approximation out of the picture. Let's do a heuristic, but with some good rules. Let's figure out the rules for the heuristic. So to do that, we first looked at like special cases of our shippers network, because they had clients who had very particular type of logistic needs. First one is a tree structure. This you observe when there is a port and they are transporting things from port to their warehouses and then to their factories. So the star network is very common. Second one, you have seen this in logistic all the time, hub spoke. So for example, Walmart has hub spoke network. They have regional warehouses that supply to, let's say, 65 stores surrounding that regional warehouse. So they transport everything between the warehouses, transshipment, and then from those to these like the retail centers. So that is the hub spoke network. So we thought, okay, can we actually solve these? It turned out we can't solve them either. So by looking at these specialized structures, we were aiming to learn something. We failed because they are still hard to solve. Then we asked, is there any way we can solve a special case of this? Because problem is hard because it has all realistic components in it. Can we relax some of them? Get some special cases? We were able to get some. I just put two. I'm not going to read through them. The reason I put them is to highlight that when there is no lane sharing cost, actually we could solve the problem. So lane sharing cost, if I can relax the assumption on that, then I can solve my problem to the optimality very easily. So I thought that, okay, this is a very good thing to have, because let's work with that. Let's come up with a heuristic, because we know lane sharing cost is not zero. So let's try to learn something from it and use that in our heuristic. So what did we do? We came up with a heuristic to solve large problem instances. And we wanted to use that to figure out what is the monetary impact and how we can actually implement this and get managerial insights. And they wanted to look at how dense the network going to be, how better the dedicated part going to be, so on and so forth. And I do not have time to go into those, but I'll show you at least the heuristic. So the heuristic had 3 steps. The first step was purely motivated by the polynomially solvable case, that theoretical result. So we actually made use of it, solve for the dedicated network. Then in the second step, we fixed certain things in that solution. And then we went to the third step and resolved the problem. When we solved the first one, we ignored some costs. In the second one, we fixed some flows. That's why we call it fix. In the third one, due to the fixing we did in the second step, the problem could be solved using a commercial solver within, I think, 400 seconds CPU time. So the initial problem could not be solved for days, but this method allows us to solve the third step within 400 seconds. So this was the heuristic, and unfortunately, I don't have any guarantees for you this time, but I can find out how good this solution is using simulation. So we coded it, we had all the real world data. So this is what I mentioned. A special case, we simplified the analysis, problem size reduced, so we resolved it. So we used the real world data, and then we actually figured out within 400 seconds CPU time, I can solve any instance I had. These are real instances, and I'm talking about this 12,000 plus network. And the gap between my proposed method and again, the bound I get from the Cplex, the word I'm using specifically is upper bound. Because in this case, we are maximizing profit, right? So your optimum solution, now it's different than the previous one. Your optimum solution is right here. This is the maximum you could do. If someone knows how to solve this problem, this is the best you can do. But your commercial solver cannot find this. It creates an upper bound. The way it works, it creates a huge upper bound. It does certain things. It does this branch and bound, and then it tries to find the best solution by reducing that upper bound. That's what your commercial solver does. Best solution, upper bound. It gradually decreases. Okay, and then when they coincide, actually there is it just check and then it tells you, yeah, you found the optimum. Unfortunately, it can't find the optimum. It gives us the upper bound only. That's all I can observe. I also don't know the optimum solution, right? So my heuristic, I know it is not going to be optimum. Obviously, it's a heuristic, right? So it's going to stay somewhere here. This is my optimum. Heuristic lives below it. My commercial solver lives above it. So the gap that you are seeing 1.88, it's between this and my heuristic. So this actually tells you this heuristic is so close to the optimum. So it's pretty good. Okay. So sometimes actually small instances, commercial solver was able to solve it, and large ones it could not. And we saw about 10% increase in profit using the heuristic, 10% increase in profit for the company by using this dedicated network. Okay, so I'm exactly on time. And if you have any questions, I am happy to answer them.
Yep. Thank you very much, Dr. Tharanga. Very interesting presentation. What we can do is now, participants, if you want to any questions, I hope there should be a number of questions. Please raise your hand using Zoom, so I will allow you to talk. Now it's time for some questions. So what we'll do is until we get some questions, Dr. Tharanga, if I can just ask you a question. This is regarding your second case with the heuristic method applied for the shipping problem, or rather the dynamic problem. Are you were you able to kind of classify the type of problems that can be addressed with this particular heuristic? I mean, I'm sure you can apply into some other cases. So what sort of other cases will apply? That is my question.
So that is where the general problem formulation helps you, because it eventually reduces to extracting cyclic. So think about any directed network. So any problem that if you can convert it into a directed network, and you are looking at directed arcs in this case. So you have to look at flows. So think about reverse logistics setting. Okay, so this dedicated idea is very unique, Prasanna. So it's very it's very difficult to generalize it to a particular a very larger context. But you can change features of this problem, so you can use a similar idea in different industries. For example, anywhere you want to do repositioning. So we were looking at a problem where it's a logistic network, and this is one of my colleagues' project, where we had these refrigerated items that need to be transported, medicine actually, for a pharmaceutical company. So they had a similar issue. They did not have a dedicated idea, but they wanted these refrigerated trucks to come back to their depot eventually. So they have to meet all these pharmacies and come back, and they had some other issues also. It's very stochastic, that network. So it's similar idea, exactly like this one. It's asset repositioning, and you have dedicated number of assets for particular type of drugs, and then you have to reposition it back. If you want to think about this one as more of a think about humanitarian setting, still you can modify this one, actually do simplifications. In humanitarian settings also, you have limited number of trucks servicing a particular disaster stricken areas. So you don't have ample number of trucks. Their capacities are known, and the parts are known. Parts are given to you, and you have to take them back to the depot. In this case, here we have FEMA. So FEMA has these FEMA warehouses from which they actually dispatch material to different like these camps, and then you have to go service them and come back. So this is still repositioning. So anywhere you see repositioning, this would work, but keep in mind that this particular problem became hard because it had this exclusivity requirements, right? So you have to use the exclusivity and the fact that empty travel is expensive. But typically in a humanitarian setting, you expect to have empty travel unless you have something to transport back. So this is a very unique situation because it's a company problem. So that's why it is very unique. It's not a high level problem we solved so that we have a lot of different applications of it.
Okay, thank you. We actually have another question from Chiran, who is asking, could you please elaborate more on the case 1, lower bound formulation? Was there a specific word to estimate the optimal condition? That is his question.
Okay, let me read it. Could you please elaborate more on the case 1, lower bound formulation? Okay. Was there a specific way to estimate the optimal condition? Yes. Okay, so if I understand this correct, if you can if your microphone works and if I am not answering your question, please feel free to ask the question again. So I think what you are trying to ask, case 1 is the robotic cell, and you are saying that we didn't use a commercial solver. So how did you come up with the lower bound? That's a lot of algebra. So whole lot of algebra. So I can actually you have access to lower bound development. I think I sent the paper to Prasanna, and there is a supplement to that where all the proofs are there. So lower bound here, what you do actually, you look at the discrete nature of the problem, and then you come up with the minimum amount of time the cell required to perform the activities. For example, in the robotic cell, aren't you going to at least have to perform all the processing? So your cycle time going to be larger than processing time, right? So add all the processing times, sum of Pj. J goes from 1 to m. M is the number of machines. So P1 plus P2 plus P3, whatever that is the total processing time. Each machine get loaded once, unloaded once, right? So that you have to add. So how many such operations you have? M plus 2 times m plus 1, because you have the output buffer and input buffer, which get handled only once. Every single machine you load once, unload once, at least in one cycle. So 2 times m plus 1 times epsilon. Epsilon is the loading, unloading time. This much you should have. Are you happy with this? No, because this is a lousy bound, right? So now you have to think about traveling time. Robo at least has to go one round, right? So it definitely goes more than that, but at least one round. So you have m minus 1, sorry, m times delta at least. Okay, delta is the travel time. Now, still this is a lousy bound because it is waiting somewhere, right? So can you figure out what is that waiting time? So that's how you develop it, but that requires you to understand what are the structural properties of it. So to answer you, it's whole lot of like thinking and whole lot of understanding the structure of the problem, and believe me, whole lot of algebra. I mean, when you look at the proof, it looks really nice and cute, but when you develop it, it's not that nice because there's no standard method to develop a lower bound or an upper bound for a given problem. It depends on your understanding and your ability to do it. And you can always come up with lousy bounds. Then my 5 by 3 approximation will become, I don't know, 8 approximation. So I have to be very careful. I have to figure out this lower bound to be as close as possible to my actual solution, sorry, optimum solution. So that is the challenge. That is why it is hard also. because the 4 cycles that you saw, it's easy to figure out the time. I mean, look at that forward cycle. You can write the cycle time by looking at it. It's very easy, straightforward. Every single cycle, explicitly, you can write the cycle time. That you know for sure, but you don't know the lower bound. So that is the challenge in the, actually that was the challenge in the entire paper. How to figure out these lower bounds, and then, of course, these 4 cycles. Why these 4 cycles?
Thank you, Dr. Tharanga. On behalf of Chiran, I think he's still having a problem with his microphone. Are there any other questions? I have now allowed any one of you to talk. Let's see, there is another. Okay, yeah, Chiran is answering you. Let you answer.
Yeah.
Do we have any more questions? You can just unmute and ask. I have allowed anyone to speak. Or either you can send in chat if you have any specific questions.
Hello, Prasanna. Shall I ask a question to?
Yeah, please.
Yes, go ahead.
Tharanga, sorry, I couldn't join at the beginning, but I have one question regarding the consultancy projects you did, because now when we try to do something similar in local industry, our industry is not ready to accept this mathematical analysis. If we talk about in terms of mathematics, especially, they don't want to listen to us even. So how you try to convince this, big companies in USA, especially, are they listening to these type of things, or how you convince them that, okay, this is the way to be optimized, things like that?
Okay, so first of all, let me correct something you said. These are not consultancy projects. I did this because, I mean, my pure PhD work, and after that also, what we actually do. So first of all, I am associated with the business school here, although I graduated with the engineering degree. So for us, when we do a project, specifically if we do realistic projects like this, it's very difficult to get a publication if it is not realistic enough, or if a company does not actually back you up. So the projects that I try to do in optimization area are always associated with either personnel from the industry or companies. First one, I was lucky. It has nothing to do with me actually, because my advisor, he has been working with this company for some time. And this company, I think Dr. Asela missed that part. It's a semiconductor wafer fabrication company, and precision matters a lot. And robo arms are very difficult to schedule because they are very complicated, and they comes with all bells and whistles and different type of criteria, processing time issues. Everything I mentioned, single gripper, dual gripper, no weight, travel time, all those complicated issues. So the company, even if they were to do a simulation, remember the even seconds saved, it's millions at the end of the year. Actually, I saw some reports, even if you save 1%, that's going to translate into millions at the end of the year. So the precision matters a lot. So they actually do implement. So for them, it matters because it is going to save them a lot of money, and they have no clue how to do this because these layouts were new at that time. So when they use it, they want to know, how am I going to schedule the movement, right? As engineers, we only schedule. Somebody gives us the schedule, or schedule him to go from 1 to 6, 6 to 4. But in this case, who's going to give it to them? There should be someone doing that analysis, and they have realized it's not efficient enough. So fortunately for me, they had this relationship, and so my advice and some other co-authors at that time, they had patents and they have implemented some of this. So that's why it worked. And why the industry listened in that case, I think because it's huge cost savings, and those were exact methods. Everything that we're proposing, they are not heuristics, they are exact methods. So they can see, you can say quantifiably, this is how much you are going to save. So they see that how important it is. There's no room for there's no wiggling space, everything non-deterministic. In the second one, it was a long story. We started off actually without the company. We saw the white paper. We thought, oh, they are doing a very lousy answer. We know better than this. Let us do this. So we started off this and we went to the review process, and the reviewers were saying it's a real problem because we quoted the company and the white paper. They said that but do you have collaboration with the company? At that time we did not. So we went to the company and then talked to so this company has an OR department. Big companies here, they have their own OR departments. They develop algorithms, heuristics, simulations, everything. So when we went to him, he actually was very nice because he's a PhD in industrial engineering. He immediately understood what we are saying, and then only problem is that he was detached from academia for a long time, and then he was trying to find these quick, easy answers to implement. Like you said, they are not receptive to big mathematical formulations. So something that you can model, put it in a commercial solver, get the answer out. So that's what actually they were looking at. So when he actually joined the project, he gave me the data, and then he realized that actually our answer is much better. So I can tell you what they were doing at that time. They did not consider lane depot capacities. They didn't consider lane sharing at all. Even the deadheading, the cost, they were just ignoring it. They were just solving a simple problem, which can be solved using Excel, I think. It's pretty easy. So when we talked to them and then included this, and actually it's not bad because they solve it and then he takes the solution out. Then he incorporate these and then manipulate the answer. Then they implement it. That's how they were doing it. So what we proposed was more like mathematical, but we gave a very simple heuristic. The first part resembles what they do to a large extent. It's a little bit better than what they were doing. In the heuristic, there were 3 steps. The first one. Second and third, of course, there's something that they have to do, but commercial solvers can actually handle it. You have to write one single code. Somebody has to code. But there is like if you are using like a commercial solver like C++, there's something called like callable library. You can use that and do this. You need either Java or C# to do it. And you can code this very efficiently. So that's what actually I did in order to get the results out. So we were fortunate, we worked with the OR personnel who was actually developing the solution. And unfortunate part was he moved out after a few years. So I don't know whether they are using anything now because it's just the person who does it. When he moves out, how well they are going to do it, I have no clue. But I have several other projects I listed, but I didn't have time to explain. One actually, we worked for a healthcare information exchange company, and that one again, we worked with the company, exactly their model, their data, everything, but they didn't implement it. They even wrote a letter for our review process saying that this is their problem, everything is correct, it's their data, everything represented correctly, but they were reluctant to implement. I think it's a lot of cost. Our work is like free of charge, right? And then for them, it's a lot of, maybe it's inertia simply. They didn't want to, and it's a smaller company also. Larger companies, if you work with them, they typically have these OR arms and they implement. I actually started a project and dropped it halfway through for a railway company. Again, the OR department. What they do is like day in, day out is what I was saying. They develop algorithms and heuristics and simulations. I mean, not random. They are like all of them have PhDs in OR or industrial engineering related back or computer science. So their OR teams are pretty sophisticated. So I think it depends on the company. Small companies, that time and the effort and not understanding what is going on, make them more reluctant to implement. The other thing is that if you go and do it and show them there is money in it, then they might do it. But I think these two, we were lucky. We were working with those companies and they knew. And we were working with people who understand what we did.
Yeah, I
But there are
think
a
you
lot
were
of
very lucky.
projects.
Yeah.
Hmm?
Because in local context, nobody is there like such a qualified persons to talk to even. So that's
Yes. So I mean, it's just for example, my husband worked for a company where they actually use these optimization methods day in day out for logistic companies, railway, airline, and trucks. So they do a whole lot of their managers come to my class to do presentations. I see a whole lot of formulations and simulations and heuristics. It's all OR. It's all optimization. And this is for American Airlines, Southwest, railways like BNSF, because here railways are not like in Sri Lanka. You use them for transportation, cargo transportation, and it's huge, the network. So they do all this yard handling, everything. It's optimization, sometimes simulation, but simulation is not like random simulation based on certain characteristics. And when they present in my class, I understand them because it's OR. It's pure OR, pure optimization. And you have industries developed around it because they come up with these methodologies, they create softwares. So I think it's just the know-how and I think you have to break the ice somehow. So here the healthcare went through that for some time. Healthcare was not doing anything, any OR. And recently they are picking up, they're understanding things are pretty bad. Cost is high because our healthcare is very costly, not free like in Sri Lanka. So now people are understanding we can better schedule operation theaters. Why didn't we do this before? So we can better schedule the appointments, we can better do that this. So there are a lot of analysis going on and people are trying to implement them. But whatever you do, I think if you give very complicated answer, they will not like it. But given the type of the company, of course. I mean, companies like Dell, Procter and Gamble, like Walmart, they are big into this. They run on logistics, so they do this day in day out. And there are industry presentations that I see in informs and even in forms. Like for example, Procter and Gamble, their network flow analysis, it's just OR. And after a while, even I lost track what they are doing because it's such a huge network, international network, and all stochastic demands. And they solve that. A lot of different methods to solve it. So if you are interested in knowing these applications, the OR part, I can send you some links where actually industry personnel present their work that they did with academicians. So they are freely available. It's just that I think link should work for you. You don't need any logging information. You have access to those.
yeah,
So you
that
can make
would be
use of
great.
them.
Yeah, yeah. Thanks.
Yeah.
Thank you, Taranga.
Okay, Dr. Tarang, we actually have another question, but I would, who wants you to elaborate more on the second algorithm, I guess he can, I suggest him to reach you offline, so that can be a more productive conversation uh, considering the time limitation. So with that, I think if there are no other questions, we can conclude the session for today. Uh, I would ask, again, thank you very much, Dr. Tharanga, for reaching us. It's good to see you after several years. With that, we will conclude the session. I would ask Subodha to deliver the vote of thanks.
Okay. Hello. Hello.
Yes, Subodha, we can hear you.
All right. Professor Thanga, before the word of thanks, I got just one short question. So this will be benefited for our students. Actually, if someone is interested in pursuing in their higher studies, postgraduate studies related to optimization, what sort of advice that you can share, give to them?
Okay, so I will take 5 minutes to give the answer then.
Yes.
Um, so it's very high level question, that's why. So what I presented, so first of all, your background should be either in engineering, mathematics, or computer science, because I think all of us can handle optimization related, work. You have the background. So, but you can do these PhDs here based on your interest and I don't know what you want to achieve in different areas. So I'm talking about US only because I have no clue about other countries and how it works. Here, every PhD takes about five years to complete, and you have qualifying exams, more than one. So if you don't pass them, you will be asked to leave. So I'm saying this upfront so you understand. I have seen students coming, and I mean Sri Lankan students failing in qualifying exams. So you can actually do OR related work in math department. You will be developing methodologies, PO theory. But if that is what you like, no problem. But being an industrial engineering graduate, I don't know whether we have that much like mathematical background unless you want to sit down and learn. Of course, you can learn, right? So mathematics, that's one. But with the engineering undergrad, I don't know whether you could get into a math department. The second stream is computer science. They also do optimization, but again in a different way. They look at the coding, how to do these things, and they develop different type of algorithms too. So, and in these days we hear machine learning, artificial intelligence. You dig into it, it's just optimization related. So if you are good at OR, not only OR, any like it's all math. So if you are good at that, you can develop these methodologies. So computer science is one way to go. Again, with the undergrad in IE, I'm not sure how capable you are to get into that. So that leaves you with either industrial engineering PhD or like a business school. So they are very similar, but in IE, most of the time you have the luxury to start a problem with a pure like mathematical sense. You can simply say consider a network the way I wrote GVE and this problem, and we solve it.
Yes.
So it's different. It's same. It can be similar type of problems, but they have more flexibility to define a problem mathematically, solve it, and get the answer out. Same methodologies, same everything. In the business school, however, because if you are doing this either to be an academician or go to the industry, right? Either way, you have to publish to get a job. To publish, you need to connect your work to industry or like business problems, or at least it need not to be like the ones that I did. Actually, I don't do all my work the way that I presented. I have very stylized models too, in optimization or otherwise. So you have to publish this work. So all the problems should be motivated by real world problems. So that's the main difference. So you start with a business story in business school. If you don't have that, forget it. You can't start with a math problem. So then you take the business problem the way that I presented to you, you convert it into a mathematical problem, and then you put all the proofs in the appendix. Basically, nobody say it. So whatever you do, your hard work, that low amount you develop, you hardly get recognized for it. But what they see is how elegant the solution is
Mhm.
and what is the impact of it on the bottom line, or whatever your objective going to be. So that is what matters. That's why that you need letters from the companies and then say that data is coming from the company if you do a real problem. If it
Yes.
is simplistic problem, still you need to link it. So to answer you, you can actually look into these four areas. And then industrial engineering and business, I think that's the best if you want to do a PhD and do OR related work. And of course, there are various other, you can do marketing. Still, marketing people also do some of them do this type of analysis. Um, but the advice would be don't forget your math. This is all math.
Yes.
Doesn't matter what you do at the end. You do a whole lot of real analysis, algebra, probability if Kanti madam is still teaching there, like everything she did that when Professor Siambala Pitya was there, that vector analysis and everything. So all those deterministic discrete optimization, I know that the courses have changed, but I think Valgampaya, maybe Dr. Valgampaya teaches, right?
Yeah,
Optimization
he's
course
doing.
now.
Yes.
So, so all those, you need all those. So if you forget them, you have to catch up fast.
Yes.
Now, having like just knowing that will not help either. You might be very good at those, but you might not be able to use them in research. So that is where many of the candidates would fail. Not that they don't know, they can't learn. It's just that they don't understand this modeling part that I was trying to emphasize on. In at least in the first one, I spent a lot of time. So that is the part that they miss. So given a problem, how do you write the math problem? That is something you have to learn. Nobody can teach you because it's very, very problem specific. So
Yes.
you should have that, I don't know, the discipline to sit down and think about it and write the mathematical statement and ability to see the similarities between math that you know and the problem you have in your hand. So that conversion process is the hardest. So of course, I didn't know any of this when I was at
Yeah, that's
Peradeniya.
true.
I loved only discrete optimization, so I thought I want to do it. But then I realized all of this going to matter after I joined. So keep an open eye, and whenever you see an industry problem in your projects and all, always ask how to represent this mathematically. And if you don't know, go to one of your professors and ask them to help you out. Or reach out if you need any help. And I think now you are getting to know a lot of professors and industry personnel. So make use of that, those connections. I think Dr. Faslina talked to you last time, and she's a very good resource. And reach out to these people. I think every one of us would be happy to help if you
Yes.
want to like understand. But if you want to like pursue PhD, actually I was asked from my department also, like if you think you want to do something not necessarily the problems I presented, something even simpler in business school, please reach out, because we are always looking for good students. But keep in mind the math background, you need that. It is
Yes.
business school, but you do math eventually.
Yeah. Thank you, Dr. Tharanga. Actually, it's really good to hear that from you. So with that, I'll move to word of thank. So very good morning to you again, Dr. Tharanga, and very good evening to you all. So it is indeed a pleasure to deliver a very hearty word of thanks to Professor Tharanga on behalf of students and our staff and all other participants. So it is actually it's needless to say how useful and fruitful today's presentation. And I think this is one of the eye-opening presentation for our students, uh, as well as for early career researchers like us. And actually, today you showed us what can be done with optimization and the way that we can look into problems and how we approach into a solution. So these, all of them are really useful and very much so that knowledge we cannot gain from anywhere else. So this is one of the rare opportunity we had today. So with this, I would like to convey our gratitude to Dr. Tharanga and for sharing your knowledge with us. Uh, and again, so this is early morning to you. So thank you for devoting your time for facilitating us. And finally, I would thank to all our students for taking this opportunity. Yes, right. So finally, have a pleasant day, Dr. Tharanga, and have a pleasant evening for all of you. Thank you.
Thank you very much.
Thank
So I
you very
guess
much, Taranga. On behalf of department, I think everybody said thanks. So very big thank from me also. Let's hope that you will be able to deliver more webinars in this mode. I think now everybody is adapted to this system so that we will be able to get more help from you in time to come. Thank you very much. Have a pleasant day. Thank you.